Okay, live is started. Okay, yeah. Hi everyone, good evening. Hope you all are doing great. First of all, thank you so much for joining us today. I am Shaishav, Surati, founder of ChaitanyaAI, and I will be your host for today's session. So, today we are going to talk about something that is becoming extremely important in the generative AI ecosystem, RAG. RAG means Retrieval Augmented Generation. But we are not here to talk about basic RAG. Our topic today is advanced RAG technique that work in production. So now most of us have probably seen or ever built a basic RAG application. You take a document, you create embedding, you store them in a vector database, you retrieve some chunks, and then you send those chunks to an LLM, and it works at least in the demo. But real question is, what happen when we take that rack system into production? So what happen when we have thousands of or millions of document? Then what happen when retrieve context isn't relevant? What happen when the user asks a complex question? So what happen when system becomes slow? And most importantly, how do you know whether our RAG system is actually giving us reliable result? That's where today's discussion becomes really interesting. So today's session is not going to just another introduction of RAGs. We are building going explore and techniques and thinking that help us to move from I build a reg chatbot to I understand how to build a production oriented reg system. So we will talk about things like advanced retrieval, hybrid search, re-ranking, chunking strategy, query transformation, evaluation, and some of the real world challenges that come when you build this system. So, and to take us through these topics, we have someone who has been deeply evolved in AI education, developer community, and the practical application of AI. So our speaker today is Nikhilesh Tayal. Nikhilesh is a Google developer expert in AI, an entrepreneur, teacher, and AI practitioner. And he is a IIT Kharagpur alumnus and has been actively sharing his knowledge with the developer and AI community through talks, workshops, and educational initiative. He has also spoken at 70 plus technology events across the globe and covering topics around AI, generative AI, AI agent, and emerging technologies. He is also the founder of AI focused education platform where the goal is to help a professional learn and apply AI in practical ways. So I think we have really great person to discuss a topic like production grade Rex. So Nicholas, before I hand over the session to you, welcome and thank you so much for joining us. We are really excited to have you here, and I think everyone joining today is going to get a lot of valuation from this session. So Nicholas, without taking much more of your time, the stage is yours.
Thank you. Thanks a lot. Thanks a lot for that energetic introduction and setting the stage.
Yeah,
Can I ask questions? Can people reply?
you can ask.
People can reply, right?
Right.
Yeah. So, so, so as we know, we'll talk about advanced RAG techniques. But let's start with some basics so that we understand. So, why? But the first question is why actually we need RAG? Like
No
why? So
audience is joined, but no one can answer here. Yeah.
anyone like so why first of all what is the like business use case of RAG? Why we want to go into building a RAG pipeline? So by the way, this is the complete rack pipeline, why we want to go into that? Anyone? Okay. So so first of all, this is what, why we want to do it. So LLM has lots of knowledge, but it does not have information which is proprietary to a company, right? So let's say, for example, any organization who wants to, build a chatbot which where it can provide the information which it has, like the company has, right? So how does it work? We actually pass the question. So we actually store that information in a vector store in the form of embeddings. The question comes, the question, based on that questions, we actually retrieve the relevant data. That data along with the question is then passed to LLM. So LLM then use that data, that context, and provide the answer, right? Now LLM mainly has two capabilities. One, yes, rank grounds AI responses in trusted data, reducing hallucination. No, that's but then why? So is this the only use case, or can it be something else? So the main is, so the main idea, so it can do all these things, but the main idea is we don't want LLM to use its own knowledge. We provide that knowledge. So LLM mainly has two capabilities. One, it has language generation capability. Second, it has knowledge. Now with RAG pipeline, we are saying don't use your knowledge. We are providing you the knowledge. Use your language generation capabilities, refer to that knowledge, and provide the answer. Okay. So and this is the whole pipeline. So we first load the data, we split it, we embed, create storage, and then when the query comes, we retrieve and we give it. So we all know this. So now the thing is, how what kind of data we can load? We can load almost any kind of data. Be it could be public unstructured data from your Wikipedia, YouTube. Be it could be your structured data like Hugging Face data set. Could be your proprietary data sitting in your uh, you know uh, presentations, your GitHub, or it could be structured proprietary data which is like your Airtable. So any from any document type you can actually load the data. So for loading PDF, we use this. Okay, this is how we load a PDF. Then we split. Now, can anyone tell me why we split the data? Why don't we directly store the documents in the vector store? Why we split? Like, what's the use of split? And if we have to split, what is the major problem or the main problem that we face? So the main problem we face when we split is that we could, there is loss of information. So when we split, and mainly we split like based on characters or tokens, it could be the case that we split the data from the middle of the sentence. Now both these chunks, now they don't make any sense. So what do? We actually do a chunk overlap to avoid this. So in chunk overlap, what do? When we create chunks, we keep a section which is common to both the chunks. So even if we have loss of data, it will the context will still remain. So for example, here what we are doing a text splitter on chunk size 4000, and we are saying chunk overlap 200. So how it will be? It will start from 1 to 4000 character. It will split, Then it will go 200 character earlier. It will start from 3801 and go till 7800. Similarly, then 7600 to 11600 and so on. So we always have that overlap of 200 characters. So the idea is to not that that information loss should not be there. So we have different kinds of splitters. Character text splitter, which is based on character. Token text splitter that we can use for tokens. Then if we have to split a website data, then we have a splitter called markdown header, because then we need to take care of headings like h1, h2, h3, which we have in a web page. Then if we have to split like code, now you cannot split a code based on character or token, because then if you split a code which has function like in between, then both the things don't make sense. And even if you add chunk overlap, that also will not make sense. So we have specific splitter called language splitter, where it actually takes care of coding split. Then we create embeddings. So what is an embedding? So embedding is basically, we represent in a 1,000 dimensional space, we provide a coordinate to a word, a sentence, or a paragraph, or a text. Now the idea here is we want to understand, we want to capture the meaning. So for example, so when we create embeddings, how do we know if two sentences or two paragraphs are similar or not? We calculate the distance between those two embeddings. And if the distance is less, we say they are similar. If the distance is more, we say they are not similar. So, for example, if we have these three sentences, like my dog Rover likes to chase squirrels. Now, Fluffy, my cat, refuses to eat from a can. So, the first two sentences are about pets. And the third sentence, the Chevy Bolt accelerates to 60 miles per hour in 6.7 seconds. The third sentence is about a car. So if you see, the first embeddings for the first two sentences are almost the same. So if you calculate the distance between these two embeddings, it would be very less. But if you see the third sentence, it has completely different embedding. So if you see here, it's like 3530, 3540, almost same. Here, if you see 58635, almost same embedding. But here, the embedding is completely different. So distance would be very large. So when we compare embeddings, we know that okay, these two sentences are similar and these two sentences are not similar. So once we create the embeddings, we store them in the vector store. So we have the document, we created the splits, we embed them, and then we store them. Okay, so this is how we do it. So we have specialized embedding models like OpenAI embeddings. We create embeddings and then we store them using FIAS. FIAS is Facebook AI semantic search. We give the chunks, the embeddings, and then we store it in the vector store. So now we have a vector store ready. And then we actually build a RAG chain. So if you see here, what we are saying, okay, whenever a query comes, retrieve 4 splits. This is the model which we are using. And then we are saying here that you are a helpful assistant that answers questions only using the provided context. So here we are saying don't use your knowledge. We'll provide you the context. Use that context to answer. If the answer is not in the context, say I can't find this in the PDF instead of guessing. Right? So don't answer, just say that I can't find it. and then we provide the context and the question. And then in the RAG chain, we have provided the retriever, the prompt, the LLM, and then this is how we build the RAG chain. So this is the again. So basically, we know about this. So now this was about your basic RAG. Okay. Now let's talk about where does it fail. So where do you think this normal RAG would fail? Anyone? What is the problem with this normal RAG? What what issues you could face in production? Anyone? Any idea? See, so the major, so the if you see here in this thing, the whole RAG system depends on this relevant splits. The better splits or the better chunks you retrieve, better answer LLM will provide. At the same time, the question, if the question is not good or the question is not proper, then you can't retrieve the relevant chunks. Now, question is not in our hands. Question users are supposed to ask the questions, and users are lazy, so they can write anything, they can make spelling mistakes, or they can do, or they don't formulate the question properly, and this is where the RAG could start failing. So this is the normal retrieval. So the first technique that we can use is your query expansion. So in query expansion, what we do, we create new queries from the same query. So when for one user query, let's say we create 5 more additional queries that can actually capture the entire context, and then we send all these queries to vector database, and for every query we retrieve chunks. So for example, earlier there was one query, we were retrieving 5 chunks. Now we have 5 queries, so now we'll retrieve 25 chunks, and all those chunks will be sent to LLM to generate the answer. So if you see here, this is how we'll use. So if you see here, right, so we have created this function called augment multiple queries. So using an LLM, we are saying this suggest up to 5 additional related questions to help them find the information, right? So now if the original query was what were the most important factors that contributed to increase in revenue, it has created, the LLM has created 5 more, which contain different keywords. So the here the keyword was increase in revenue. So the first one was first, okay, what were the key revenue drivers? Second, you can see how did pricing strategies impact revenue growth. Third is any new product launches. Fourth is did any acquisition or partnership play a role, and how did changes in customer demographics. So so now we have different queries that capture different intent, and here then you add these augmented queries to the original query, and then you retrieve. So you have, instead of 4 or 5 whatever you have, so here we are saying end results 5. So for every query we are retrieving 5 chunks, so now we have 25 chunks. So we are actually retrieving more information and giving it to the LLM. Now what is the problem with this approach? When we retrieve more chunks, what could be the problem with this approach? Problem is that we are giving more context, and more context means more money. So for the same query, now we are incurring 5x amount. Our costing increases by 5x for the same query. Now that's not sustainable. So what is the solution? We use cross encoder re-ranking. Basically, once we retrieve the results, we what is me? Yes, chunk. See, we covered this. So chunk is this. So here, see, when we retrieve, this is the chunk. This is, split is the chunk. Basically, we store chunk is like one kind of one paragraph. So we have a huge document. Let's say we have one PDF with 10 pages. So what we'll do, we'll divide those 10 pages, each page into, let's say, four chunks. So it would be like 40 chunks. So now that PDF will be converted into 40 chunks, or basically 40 splits. And then we embed each chunk and split, like, we create embeddings for each chunk or split, and then we store. Is it clear now? Like, have I answered your question? So I missed the previous message. Can you please send it again? Like, okay. So we talked about query expansion. Query expansion, where we actually convert one query into multiple queries, and then we are retrieving more results. Now, sending more results means more money. So, what is the solution? Now, what we'll do, we actually re-rank the chunks based on the relevancy, and we use a specialized model called cross encoder for that. So now you can see when query comes, we retrieve results, and then these results are then re-rank based on the relevancy. So we had 25 results, 5 results per query, but we want to send 5 only. Like out of 25, we want to send 5 only, or 10 only. Then we use this model cross encoder and we re-rank it. So you can see here we have used a cross encoder, this specific model MS Marco Mini LM. So it will provide the score, how relevant that all these queries are, like the chunks are for to the original query. You can also order them or basically rank them, and then from this ranking you can actually decide how many queries to send. So this is how we do it. We solve the problem of more context. Any questions so far? Now the third technique is filtering with metadata. So when we retrieve RAG, when we do RAG, when we retrieve information, we also retrieve metadata. So we say that RAG, we reduce hallucination. The response is more grounded. It's because we can always double check with that metadata. So you can always check that this. So LLM will always provide you the information about metadata. So let's say you ask something, like for example, you have built an HR chatbot, and then a user comes and asks, okay, what is your maternity policy, maternity leave policy? So in that case, let's say if LLM, we retrieved the result, so then LLM has the information, okay, from PDF 2 page number 3 this chunk has been taken. So this metadata information is always there with the LLM. Now, in some cases, we need that metadata. Okay. So, for example, here, so let's say if the query is, I would like to book a listing with seaside view, nice restaurant, and a capacity of 3 bedrooms for 5 adults. Now, here, these numbers are very important, the 3 numbers for 5 adults. But if you see, you have applied the RAG. Now, in embedding these 3 and 5, they don't matter much. Embedding is more on the similarity of words, the meaning. So 3 or 5 doesn't matter, like they don't matter much. But in this query, these are the main filtering criteria. So if you see here, this entry where bedrooms are 6 and it can accommodate 6 people have also been retrieved. Now, this is completely irrelevant. So, what do we do? Once we do the retrieval, we apply metadata filtering. So, now we actually filter with the actual numbers. And when we filter with the actual number and the C side, then we get the right result. So, this is the process. So, we apply the vector search and then we do a filter to get the relevant results. So if you see here in the code, when we are applying vector search, we have done the retrieval, and then after that we are adding a filter where we are saying, okay, accommodates 2 bedroom 7. So now we are also adding a filter. Okay. Another technique is that now when we retrieve the result as well as the metadata, there is lots of information, and when there is a lot of information, again we are actually incurring lots of money because we are sending more tokens. So how can we reduce the number of tokens? So one method is projection. So in that, what we do, instead of retrieving all the metadata information, we actually specify which metadata is actually relevant to us. So now we say, okay, only don't retrieve all other information, only retrieve these 3 information, that what is the title, medium, date completed, only this. So this is how we save on tokens, because other information like ID, artist, dimensions are not relevant to us for this, for the current query or for the current use case. So here, this is how you add. So in the projection stage, wherever you are, whenever you say 1, that metadata information will be retrieved. Wherever you say 0, will not be retrieved. Any questions so far? So then we have another method called sentence window retrieval. Here, what we do, so the problem is that for this question, and if this is the chunk or this is the paragraph, the answer which is actually relevant is here, only one sentence or maximum 2 sentences. But for these 1 or 2 sentences, we are actually sending this whole paragraph or the chunk, which is again wasting our money. So another retrieval method is that instead of embedding the whole paragraph, embed sentences. And then when we are retrieving the sentences, send sentences which are before or after that, or that the relevant sentence. So this is a technique which is proposed by Llama Index, and they have given this sentence window node parser. So if you can see, we are saying window size equals to 3. This means once you do this, the node will be created like this. So if sentence 4 is the relevant sentence, 3 sentences before that and 3 sentences after that will be sent. So earlier, let's say if one we were sending 5 paragraphs and each paragraph has, let's say, 5 sentences, so we were actually sending 25 sentences. Now we are only sending 7 sentences. And in case if the sentence 1 is the relevant one, then we don't have to send anything before. We'll only send 3 sentences after that. And same is the case with sentence 7. We don't send anything after, only send 3 sentences before that. So this reduces the context size drastically. So if you see the difference between normal RAG and sentence, in normal we retrieve chunks, in sentence we retrieve sentences. If you see here, chunk may contain lots of unrelated text. In sentence, the matching sentence is very precise. And then the context comes from the chunk itself. Here we add the context through neighboring sentences. Embedding is actually at chunk level, and here embedding at sentence level. And now we have the last technique, which is auto merging retrieval. In this technique, what we do, we divide a bigger chunk into smaller chunks. Okay. Now, if this chunk, so how do we retrieve? We retrieve that if one chunk is retrieved, then this one will go. If two chunks can be retrieved, then two will go. But the moment it has 3 or 4, they will actually auto merge, and instead of sending them it individually, we the bigger chunk or the parent chunk will be sent. So if you see, define a hierarchy of smaller chunks, and if the set of smaller chunks linking to a parent chunk exceeds some threshold, so you can say threshold could be like 60%. So with one chunk is 25%, with second chunk is 50%. Now with the moment third chunk, now it exceeds 60%, which is 75%. So the entire chunk will go, the merge. So it will not be sent. So that's how we actually save on. So how do we do this? We use this hierarchical node parser. So we are saying chunk sizes 2048 will be divided into 4 of 512, and then each 4 of 512 will be divided into 4 of 128. And then when we are retrieving it, once if the threshold reaches, it will send the entire thing. And if you see how effective they are, so auto merging groundedness is almost 100% sentence and then direct. So it's much better than direct query engine. In terms of relevancy, then also auto merging is better than not direct. Context relevance improves significantly with auto merging. Latency slightly increases because we are adding an additional step. But in terms of cost, you can see we save a lot of money here. At the same time, we also increase context relevance. Yeah, that's it from my side. If you have any questions, I'll happy to answer. Yes, it's a good question. So best chunking strategy is, so we don't have a best practice yet when it comes to chunking strategy. it actually depends on the use case, like what kind, how much, what kind of rack system you are building. So actually that depends on. So far we don't have, but chunks are like you create smaller chunks, linked it to parent, create chunk overlap, those kind of things you can do. No, it cannot completely eliminate hallucinate. See, hallucination is actually intrinsic nature of LLM. It's not a bug. So if it's a bug, we can actually identify and remove it. But hallucination is like their nature, like like make for like when we say that humans make mistakes, to err is humans nature, to make mistakes is humans nature, to hallucinate is LLM's nature. So we cannot completely eliminate hallucination, but using these engineering techniques we can reduce them. Yes, millions, I would say. Let's go to billions. So what do you think first? What is your, what, how will you consider if you have, let's say, I'll further increase the stake, you have billions of documents instead of millions. What how would you think, what is the first thing you will do while designing the RAG architecture? So when you want to scale RAG, multiple problems that can come. So one problem can come is you can't rely on one vector, when one vector database. So you have to create replicas of those. That's one. Second, so basically for everything you need a backup. That's the thing. Like you need to think from the management perspective now. So this is more of management than technology. So you create multi-region vector database backup. That's one. Then you rely on multiple indexing. So if one indexing can fail, you go for another indexing. Third, if now if you are using, like if your retrieval fails, as in your semantic search fails, then you fall back to your keyword search. That's the third thing you can design in your RAG architecture. Fourth, if it's multimodal and you are retrieving images as well, then you have to fall back to text retrieval. So that's the thing. So basically, when you have millions or billions of documents, you need to create a system where everything you have backups and multiple backups, so that if one system can fail, system can actually go to the other entity. Any more questions? We discussed, right? See, accuracy. So we discussed right here. So with auto merging, you can see we have improved the accuracy and the cost, but we have slightly increased the latency. So improving all these three are actually impossible. So you can increase two, and you have to like trade off with the third one. So now you need to think which is your, like which one you will prefer. Yeah, that's also very good question, that how should we evaluate. So one method is LLM as a judge. How you evaluate is LLM as a judge. So you build a rack system using one LLM, and then you use another LLM to evaluate, right? At the same time, we have to continuously evaluate our cost, our latency, right? What should we measure is the same, right? Accuracy, cost, and and your latency. These three things we have to measure, right? Now, when it comes to accuracy, we have to measure two things: whether we have retrieved the right results, and second, whether LLM has generated the right response. These two things that we have to measure, and for that we use LLM as a judge method. We use one method to create rag pipeline and use another to evaluate it. But yes, we have to continuously evaluate, and we have to use another LLM. We could add the latest model, or we do indexing. We work on this thing, latency, all those kind of things. I hope I have answered your question. Any more questions? Are we done?
Yeah, I think done. Yeah, no question.
Cool then.
Yeah,
Yeah. So
yeah. Yeah, all right, everyone. I think we have reached the end of this session. So, first of all, a huge thank you to Nikhilesh Bhai for taking the time to join us and for sharing such practical insights on advanced rec technique that work in production. So, Nikhilesh Bhai, I think the biggest takeaway from all of us is that building a rag demo is one thing, but building a reliable, scalable, and production ready system is a completely different challenge. For that, thank you for making this concept easier to understand and for sharing your practical insights with us.
thank you. Thanks for having me.
Yeah,
Yeah. Thanks. Bye.
thanks. So, whether you are a student, developer, AI, ML engineer, founder, or someone exploring generative AI, I hope you are taking away at least a few ideas that you can eventually apply to your own project or your corporate work. And this is not the end. At the Chaitanya AI Academy, we are going to continue bring more practical session around generative AI, LLM, AI agents, RAG, and real world AI engineering. So, if you found today's session useful, make sure you follow Chaitanya AI Academy as well as subscribe our channel and stay connected with us for upcoming sessions. Also, if you are enjoy this today's session, please share it with someone who is currently learning or working with RAG and generative AI. Once again, thank you so much, Nicholas. Bye. And thank you everyone for joining. Have a great evening. This is the Shaishav Surati sign off and see you in the next Chaitanya AI Academy session. Good night, everyone.